Hi everybody. In today's lecture I'm going to do a couple of examples and show you how to code some simple vector operations and also how to handle angular momentum and torque in VPython modeling. So first of all, this might be a bit of a review, but also some update with some new values. Remember that if you're dealing with vectors in VPython, that there's a lot of vector operations that can be kind of time consuming to do by hand that you can do with just one short little command in VPython. So once we've already covered, including finding the magnitude of a vector. So for example, if you've named your vector A, you can find the magnitude of the vector, which is of course the square root of the sum of the squares of the components, with just the command mag of A. Okay, so mag, parentheses, A inside. That's it, one line. The unit vector can be found in a couple of different ways. The one that I show here in today's example is norm of A, okay? And that gives you the unit vector associated with the vector. Another one that's common is hat A. Hat meaning, of course, the little caret hat that you put on top of a unit vector to indicate that it's a unit vector. And then today we're going to cover a couple of new vector operations. So if you have two vectors, A and B, of course you can multiply those two vectors in a couple of different ways. If you multiply two vectors and get a scalar, then that's a dot product. And if you multiply two vectors and get another vector, that's a cross product or vector product. So if you want to do that in VPython, we've covered in a separate lecture how to do it by hand. But if you want to do dot product in VPython, then it's very simple. It's just dot of A comma B inside the parentheses, one line. If you want to do the cross product of two vectors, same kind of thing, cross of A comma B. So I've got an example code here that shows how to do these things. So let me pull that up. I've got all my problems here on my public page so that anybody can access them if they want to get a little example. And I've called this one dot and cross products. So let me pull that up. Okay, so first what I do in this simple program is to visualize the vectors as arrows. So I've got a vector A and a vector B, and I do vector A in red and vector B in blue. Vector A I put at the origin, so remember when you're doing arrows you use the command arrow, and then you specify the position of the beginning of the vector, pause, and that's I put at the origin. And then the axis of the vector is the vector's components. And so vector A is 2i hat plus 3j hat plus 4k hat. And so I've done that, axis equals vector 2, 3, 4. I've made it red, color equals color.red, and I've specified the shaft width as to be the same for all vectors as 0.5. And then I do the same thing for vector B, okay? Its axis is 1i hat minus 2j hat minus 1k hat. But it's similarly positioned with its beginning at the origin. Now next, I want to calculate the cross product of vectors A and B. Now since I've specified vector A and B as an arrow, then in order to do the cross product, I have to call it via the axis attribute. And so to do that, I've called vector C axis. So C here, I'm going to have A cross B equals C. Okay. So the axis of vector C I've called, not very originally, C axis, and it's cross of A dot axis comma B dot axis. So that's how you do that if you're calling an attribute. And then I'm going to visualize vector C as an arrow, and I'm going to make it a purple arrow because red and blue make purple, and I'm telling it that its position is also at the origin and the axis is C axis, which I just specified up here. Okay, so if I run my program, there they are, vector A and vector B in red and blue, and then vector C is in purple, and as you can see, as you expect, your cross product vector is perpendicular to both of the vectors that go into making it A cross B. So A and B are both perpendicular to C, which is purple. Okay, so that's the first bit. Now, if I wanted to calculate the dot product, of course that's not a vector, it's just a scalar, but I can calculate it, and then down here I make it print the value for you. So I'm going to have D be the dot product of A and B, so that's the dot of A dot axis, comma B dot axis. So that's how to do that, okay? And then if I wanted to find the unit vector associated with vector A, or with any of the vectors really, I could just use the command norm or hat. Here I did unit A is equal to norm of A dot axis. So that's how to find that unit vector, okay? Now, I could also find the length of various vectors. I call those L underscore A, L underscore B, and L underscore C for lengths of vectors A, B, and C respectively. And I do that with the magnitude command. So that's mag of A dot axis, mag of B dot axis, and mag of C axis. And that finds the magnitudes of my 3 vectors. All right. Now, sometimes questions might ask you to find the angle in between 2 vectors from either a dot or a cross product. Remember that if you do A dot B, that equals D, for example, that the angle in between A and B can be found because the magnitude of D is going to be mag A times mag B times the cosine of the angle in between them. And if it's a cross product, then the magnitude of the vector cross product, which would be the magnitude of C, would be equal to the magnitude of A times the magnitude of B times the sine of the angle in between those 2. Okay, so we covered all that in the previous lecture. So if I wanted to calculate the angle in between vectors A and B, then I could use that formula for my, for example, cross product is what I did here, and calculate that angle with an inverse sine. So the angle in between A and B I called theta AB radians, okay? And it's radians because remember that the default for VPython is to report angles in radians. And if you want to get it in degrees, you have to do a little bit more work. Okay, so here theta AB radians would be the inverse sine, which is in VPython a sine, okay, of the magnitude of vector C divided by the magnitudes of vectors A and B. Okay, so there you go. That's how you find your angle in between those vectors. Now that is in radians. If you want it in degrees, you could just do the conversion, which is that pi radians is equal to 180 degrees, and then multiply and divide by the numbers as needed to get from one to the other. Or you could use the simple VPython command. Okay, so if I want to know the angle in between A and B in degrees, I could use the command degrees. And then what you put inside the call parentheses is degrees of the angle in radians. So for here, the variable is theta AB radians. So it's degrees of theta AB radians, and that would convert that angle, which is in radians, to degrees for me. And then here I just have some print statements that will output what my values of my numerical things are, like my dot product, my unit vector, and the angles in degrees and radians. So if I run the program again, you can see the print stuff is down here at the bottom. See? And it tells me what my, dot product of A and B is. D is -8. The unit vector associated with A, which I asked it to calculate, and the angle in between A and B, which is about 53 degrees, okay, or 0.92 radians, okay. So that's a nice example program for you to use if you want to refer back to it. And remember also that you can always go to the help pages. I show that here. The link to the help pages is here. And so if you want to put that in here, you can see these help pages. I refer to them all the time myself. And you can access them off glowscript.org, and the help menu will be in the upper right hand corner. Here I've gone ahead and called the help for some math operations, and there they are. There's a list there, kind of a laundry list with some examples. But if you need to know anything, then you can use these drop down menus right here to look up any of the commands that you might need in VPython and find them there. Okay, so that's very helpful, and I encourage you to use that resource. Okay, so now that we've reviewed how to do dot and cross products in VPython, let's go ahead and talk about modeling torque and angular momentum. All right. Now I'm going to assume that you already remember the stuff about torque and angular momentum. If you don't, you need to go back and watch those lectures for a little review. But just in general, remember that the angular momentum L is equal to r cross p, where r is your position vector and p is your momentum vector, and that your torque, your tau, is equal to dl dt, which is the time derivative of your angular momentum. So those things are there. Okay, so that's the relationships that you might need to know to understand this stuff. Okay, so what we're going to be doing is modeling a problem in matter and interactions. It's actually problem 86 in chapter 11, and I'm going to show it to you in a second. But what we're going to be using is the iterative technique, okay, and the iterative technique is generally using a loop to update changes in either position or angular position or what have you within the loop from forces or torques that are happening in the system. So it's important, though, for the loop to work in order to specify the initial conditions and important constants that you need outside of the loop in the front matter. So you specify those things first, and then you move into your loop. Now, what goes in front of the loop? Well, remember, initial conditions, initial values, and also any constants that you need to specify, okay? Anything that changes in time needs to be either updated or calculated inside the loop. But your front matter will definitely include things like masses, dimensions, initial positions, initial values, moments of inertia, your time step size, your initial angular momentum, the initial values of time, the initial values of the angular velocity and position. All that stuff needs to be specified before the loop, and then you can update the values as needed within the loop. Okay, so what goes inside the loop? Well, anything that changes must be updated or calculated inside the loop. So that includes, first, since this is an angular momentum problem, the first thing that you're going to do is calculate your net torque, okay? Now, your net torque could change, okay? In fact, it will change in your homework problem, excuse me. But it could also be a constant, as in the example problem that I'm starting off here. So, but first of all, you need to calculate your net torque. Then you need to use that torque to update the angular momentum of the system. Now remember that torque is equal to dl dt. But that means that over a very short time step, you could approximate that torque as constant, even if it's not, just over a really tiny little time step. Okay, remember your calculus. And so that would mean that you could use your angular momentum update equation, which is that the angular momentum now, L final, is equal to your old angular momentum, L initial, plus the torque, tau, times your time step delta t. Okay, so that will update your angular momentum. Now, from that updated angular momentum, you can now calculate your updated angular velocity. Omega is equal to L over I. Remember that angular momentum, L, is equal to I omega. Okay, so you can calculate your angular velocity, and then you can use your angular velocity to calculate the change in the angular displacement that you've got, delta theta. And that's going to be equal to omega times delta t. And your new angular position would then be your old angular position plus that change in angular position, delta theta. So you could write theta final is equal to theta initial plus omega times delta t too. All right? So that's the kind of thing that needs to go within the loop. Okay, now if you want something to rotate in VPython, there's an easy command, of course, that can be used to make that happen, and it's called rotate. Nice, huh? So the rotate command, you can learn more about it on the help menu if you'd like. I'm going to do an example problem here in a second and show you how it's used. And I copied the line from that example program here just so you can get an idea of what we're going to do. So in this code that I'm going to do, I have an object I called rod, and I'm rotating that object rod by an angle in each time step, d theta. Okay, I specify what d theta is in the code. It's a variable name. And then I'm going to rotate it about a specified axis of rotation, which I've called in the code axis of rotation, axis underscore of underscore rotation. I'm not very original, right? And then the origin that it rotates about is going to be an axle. Okay, I've specified that with a variable name here, axle. Okay, there's an object defined within the code called axle. And then I call on the position attribute of my object axle in the code. Okay, so that's what I'm going to do. So I'm going to show you my code, but first I think what I'll do is I'll describe it and I'll read the question to you. So there's the link to the code if you want to pull that up. It's going to model a rod on a low friction axle. The rod's going to start off initially at rest, and then a constant torque is applied. And then it shows the rod rotating about the axle, and it also shows plots of the angular displacement and the angular velocity of the rod's rotation with time. So this is parts A and B of problem 86 from chapter 11. You're going to use this as a starting point, and you're going to do parts C and D for homework. Okay? So let me pull up the question. So here it is. It's from Chevet and Sherwood's Matter and Interaction. And it reads, a rod on a low friction axle is initially at rest when a constant torque begins to be applied. Complete the skeleton program shown below and make sure that it runs properly. See section 11.10 for suggestions. After exiting the loop, print the values of the final angle theta and the final angular speed omega. Given the fact that the torque is constant, what should the value of mag omega over theta be? Is this true for your program? And make graphs of theta versus time and your angular speed versus time. What should these graphs look like? Do they? So that's the part that we're going to do here. I'm not going to answer all the questions. I'm going to leave that for some imagination, but I am going to show you the code here. So this is the code that they wanted us to start with. This is the starter code specified in problem 86. So let's talk about this. The rod is a rod of mass 2 kilograms, of length 1 meter, and it has a radius of 10 centimeters or 0.1 meters. The axle, which is visualized in red, the rod is visualized in orange. The axle has a length of 4 times r, which was shown here. The moment of inertia of the rod is 1/12 the mass of the rod times the length of the rod squared plus 1/4 times the mass of the rod times the radius of the rod squared. Now, you might be looking at that going, huh? Right? Because we, in class, modeled the moment of inertia of a long, thin rod, and we said that it was 1/12 ml squared. But if you look here, this is some plots of different moments of inertia for standard objects. And you can see that while that is true, that 1/12 ml squared is true for a thin rod, right? There's 1/12 ml squared for a thin rod. If you have a fat rod, for lack of a better term, then you need to add in the contribution from how fat it is, the mr squared over 4. Okay, so that's there. Okay, so that's where that comes from, and you can derive that expression if you want to, but that's the one that they're using in this program. Now, it visualizes the rod as an orange cylinder. So here it is, rod is equal to cylinder. They put it initially at -1, 0, 0, so it's on the x-axis at -1. Give it a radius r, which they specified up here, made it orange, and had its axis point along the x-axis and of length L rod. Okay, so that's that. And then the axle is going to be pictured in red. See, it's colored red. And its position is shown here so that it runs through right through the middle of the rod there. Okay, so the position is specified so that it runs through the middle of the rod, and it gives it a little radius so that it's actually spinning so that it doesn't, go fatter than the orange rod, and it shows the axis there, and it's along the z-axis. Okay, so the orange rod is initially positioned so that it points along the x-axis, and its axle is piercing through it this way, coming out in the z. And then they specify the front matter. It's going to start from rest, so its angular momentum is initially 0. It's going to start not rotated at all, so its initial value of theta is 0. And then since it's starting from rest, the initial change in angle d theta is also 0. We're going to start our clock at t is equal to 0, and we're going to make our time step 0.1 milliseconds or 0.0001 seconds. And then they show you the beginning framework for the loop while t is less than 2, so we're going to run the loop from 0 to 2 seconds. There's the rate command, which allows you to visualize it well without looking jerky and crazy. And then it shows you that we're going to start off with a constant torque. Okay, so the torque is going to point along the axis of the axle. Now remember, that's important. If your torque is not along your axis of rotation, then you're going to get some wonky kind of wobbling in your rotation. You don't want that for this problem. And so we're going to have the axis and the torque point in the same direction. And then it tells you what to do here. Apply the angular momentum principle, update the angle in the rod position, and increment your time step. So that's what we're starting off with. Okay? So that's the question. And now let me show you what we did here. Oh, sorry. Let me show you what I did here. So I'm going to go back. This is my Chapter 11, Problem 86 code. So here it is. Okay, so there's the front matter that they showed you in the code. I copied and pasted it there. And then within my loop, I filled in for the parts that it asked us to fill in for. But let me run it for you so that you can first see the rod rotating. Okay, so there it is. You can see that the rod is orange, the axle is pictured in red. The rod initially starts along the x-axis there, as you can see, and then it starts to rotate about the z-axis. Okay, so the rotation takes place in the xy plane, and the axis of rotation is in the z. Okay, so let's go back and talk about that now. So focusing in on the parts that the question left out, this is where the question left off. We specified our constant torque, and now remember, going back to our iterative technique, what you do within the loop is you calculate the torque, you then use that torque to update your angular momentum, then update your angular velocity, and then update your angular position. So that's basically your steps there. And so if we do that here, what I've got is my, let's make this bigger so you can see it a little bit better. Okay, so here's my torque. Then I use my angular momentum update equation. I'm saying that my angular momentum L is equal to the old value of L plus my torque times my time step delta T. And then I calculate my angular velocity omega, which is going to be my angular momentum L divided by the moment of inertia calculated up here, right? Now, here's the thing. Angular momentum is a vector, and I'm dividing that vector by a scalar, which means that my result omega is a vector, okay? But for easy operation, what I want to do is use it as a scalar quantity. So I'm going to find the scalar value, or my angular speed there, by taking the dot product of my omega with my axis of rotation. Now, just so that it's more general for later, because later you might have a question where the axis of rotation is not a unit vector. But see here, I specified my axis of rotation as being the z-axis, 0, 0, 1. Okay, so I didn't necessarily need to do that for this problem, but I left it general so that you could use it later. Okay, so this gives me the scalar. Remember that when you do a dot product, you get a scalar result. If you do a dot product of omega with your axis of rotation, then that will give you your angular speed. Then from my angular speed, I calculate my change in theta, d theta, which is omega scalar times delta t. And then from that, I can calculate my new updated angular position, which is theta new is equal to theta old, or theta is equal to theta plus d theta. Then I tell my rod to rotate. Okay, so I've got rod dot rotate. How much? By an angle d theta, right, that I just calculated. About what axis? Well, about axis of rotation. And where is all this taking place? About my axle's position, axle dot pos. Then what I've done here is I've got a couple of plots that I called before the loop, that I defined before the loop. I'm plotting my angular position theta and my angular speed omega, right? And so then within the loop, I tell it to add a new data point to those plots. Theta plot dot plot is the t comma theta, so it's plotting the angular position versus time there. And then my angular speed versus time, omega plot dot plot. Then I increment my time, and I get out. So running it again, there's my rotation for 2 seconds. And then if I go down here, you can see what my plots look like. Okay, so remember, in the red is my angular speed, and in the green is my angular position. Okay, now this is a constant torque situation, right? Constant torque. Constant torque means a constant angular acceleration. A constant angular acceleration means a linear change in my angular velocity, which is what we see here. Okay? All right. I hope that gets you started. Now, what you're going to do in homework is, those are parts A and B of the question. You're going to do parts C and D, where you have a torque that is not constant. Okay? So that's what you're going to do. Let me know if you have any questions about the homework. I hope that helps and gets you launched, and I'll see you in class.